Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to talk about a method that we've been hinting at for a couple of videos now. It's how we deal with some of the trickier limits where we've had to come up with some inventive methods. It's called L'Hopital's rule. This is L'Hopital's rule. Now, before we discuss the rule, we need to go ahead and address what exactly is an indeterminate form and why do they come up. So, you probably notice that there is a pattern here, and that is that an indeterminate form generally involves either 0 or infinity. And that's because 0 is kind of the weirdest number. It's got special rules like you can't divide by 0, which is why we have the problem here and the problem here. And then infinity is interesting because it's the concept of going on forever, but it's not actually a value. So any time that we would have to be using it like a value, it's going to cause us a problem because it does not have a fixed concept of what's going on. It generally is doing something, but in doing that thing, we don't know what's kind of happening throughout the whole duration. So we can't know where we're at during each basically iteration or each step along the way for these kinds of infinities. Okay? So for L'Hopital's rule, we specifically care about infinity, or rather these indeterminate forms. And what we're going to learn is how we can take these indeterminate forms and try to shift them into looking like this so that we can apply L'Hopital's rule. Because if we can't do that, we can't use L'Hopital's rule, and there are other different, more powerful methods that we're going to learn later, or we'll have to use some of the methods that we've previously used, such as the squeeze theorem. Now, here's L'Hopital's rule. Suppose that f and g are functions that are differentiable on an open interval I that contains the value a. They don't have to be differentiable at a, just like our normal limit definition. And that the derivative of the function g of x is not equal to 0. That's important. Okay? So if we let capital F equal the quotient of the function f of x over g of x, then if the limit as x goes to a of capital F of x is equal to either 0 over 0 or infinity over infinity, then we can say that this limit would be the limit as x goes to a of the quotient of the derivatives of f of x over g of x. Now, where L'Hopital's rule comes from is the idea of our linear approximation, and we apply a kind of more generalized version of the mean value theorem. Told you it'd come up again. Although this time it's Cauchy's version, where instead of looking at a specific one function, we actually look at two functions. We look at the difference of functions, or in this case, we look at the quotient of functions. And we go through the same exact process we did to prove the normal mean value theorem, but the more generalized mean value theorem is instead of using a point A and a point B, we use two functions that meet each other. It ends up working out the same exact way. But in using that, we're able to come to this conclusion that the derivatives of these two functions, if they're differentiable, will actually approach these values. Now, what's nice here is that if we can get our function to look into one of these two indeterminate forms so that we can apply L'Hopital's rule, we can actually continue to apply L'Hopital's rule until we get an answer. So for example, let's say that we have a situation where we get, 0 over 0 for something. And then we take the derivative. And when we take the limit of those derivatives, we still get 0 over 0, or infinity over infinity. We can then reapply L'Hopital's rule and go again. And remember, the advantage here is that oftentimes one of these two functions will be getting more simple as we go. Maybe one of them is a polynomial, and so its degree will be decreasing. And if you continue to take the derivative of a basic polynomial, eventually it becomes a constant function, which is just the derivative of 1. And that's the reason why it's important that we say that the derivative of g of x can't equal 0, is because if we have a constant down here, we can't then take the derivative again, because then that derivative will always be 0, and there's no way that we can actually continue to apply things, and it just becomes undefined, rather than indeterminate, because the limit as we approach here is the issue. But if you're always 0, then that limit doesn't matter because you're always 0. So you are simply undefined rather than indeterminate. And that's kind of why we have that difference. So let's look at some examples of problems that we've actually previously solved and how L'Hopital's rule applies. So here are two examples that we looked at in previous videos. The first one over here, sine x over x, is one that we proved, like it says in the bottom, geometrically using the squeeze theorem. And then over here is one that we proved much later when we were talking about taking the limits as x approaches infinity in our horizontal asymptote section. However, both of these qualify for L'Hopital's rule because if we simply take the limit, you'll notice that sine x is 0 and x is 0, so we get 0 over 0. Applying L'Hopital's rule, we take the derivative of sine x, which is cosine x, the derivative of x, which is 1, and then when we take the limit as x approaches 0 of cosine x over 1, we get 1 over 1, which is 1. Now, it's important to notice that we are not taking the derivative of the quotient. We are taking the quotient of the individual derivatives. So we're not applying the quotient rule here. We do have to take these as individual pieces. This is a different situation. Please do not get them confused. Okay, over here on the second one, again, we know that we can solve it this way. This is a perfectly acceptable method of using. However, in this situation, let's apply L'Hopital's rule because it looks like it qualifies. So if we take the derivative of our numerator function, we get x squared minus 1, the derivative is simply 2x. We take the derivative of our denominator, 2x squared plus 1 is simply 4x, 2x over 4x. Now, just because we're taking the quotient of the derivatives, we can still go through the same algebraic simplification after the derivatives. So when this simplifies, those x's go away and we get 1/2. So when we take the limit as x approaches infinity, well, there's no x's here, so that it doesn't matter. And so the answer is simply 1/2. Exactly the same thing we get here when we use our factoring method so that we can apply our theorem that says that when x approaches infinity of 1 over x, we get 0. So as you can see, L'Hopital's rule can simplify things that previously might have taken us a lot of work. It is important to note, though, that you can only use L'Hopital's rule specifically if you can work your function into a situation where it will be 0 over 0 or infinity over infinity. Infinity over 0 doesn't work. 0 over infinity doesn't work. There is a situation that students often get into where they think they have an indeterminate form and it turns out they don't. For example, if you have infinity times infinity, that's just infinity. That's not indeterminate. Both numbers are growing forever. It's simply infinity. Or if you have infinity times negative infinity, that's again simply negative infinity because you're saying an infinitely growing positive number, an infinitely growing negative number. A positive number times a negative number is a negative, and that's the only thing that really interacts in that way, so you get negative infinity. Similarly, if you have positive infinity plus positive infinity, it's infinity. So let's look at some actual problems where it's a little trickier to solve. So go ahead and attempt these 4. They look very similar, but I will warn you, one of them you can't apply L'Hopital's rule to, and one of them you're going to have to work with before you can apply L'Hopital's rule. I'll show you how these are worked out in 3, 2, 1. So how'd you do? Now, the first two are pretty straightforward. The first one is simply a direct application of L'Hopital's rule. We already have 0 over 0. We hit it with L'Hopital's rule one time. We get our limit is equal to 1. Our second one, also pretty straightforward. We have infinity over infinity, but when we take L'Hopital's rule, we end up with infinity over infinity again. However, that still qualifies for L'Hopital's rule, so we simply apply it again, and we get to infinity over 2, which is not indeterminate. That just means that we go off to infinity. Poof, our, equation runs off forever. No big deal. When we get to number 3, this one's a little trickier because at first we don't qualify for L'Hopital's rule, But we notice that when we have a 0 times an infinity situation, we might actually be able to do something with that. Because if we have 1 divided by 0, we know that runs to infinity. So if we're able to rewrite this using that knowledge, which luckily with this one we can put it into a system that will fit L'Hopital's rule, and then we can take our derivatives. Now, you could also have done it the other way and gotten 0 over 0, but that might have been a little bit trickier. Feel free to try it if you'd like. Typically, like with most things, you want to try to take the path of least resistance when you can. Although, as we'll find later, sometimes the path of least resistance will run you in circles. Not with this, though. And then on our last one, this one doesn't qualify for L'Hopital's rule, but unlike the other one, this isn't a division situation. And there are a couple of ways you can look at this one. And one of the things that you can look at with this one is that it's pretty straightforward in the fact that we know that this is running off forever getting large, and this eventually runs to just becoming smaller and smaller values. So you can kind of work your way around to understanding that you're going to be going to negative infinity, but you can also simply take your limits to demonstrate that you will by rewriting it as a multiplication problem. And then when we apply our limit rules, because we have infinity times negative infinity, we know that this will be negative infinity, and so there we go. No need to apply L'Hopital's rule at all. And in fact, it doesn't even qualify for L'Hopital's rule. If you attempted to do that, you would end up running yourself around a bunch. So, I'm going to leave you with a few exercises for you to try yourself now. So I hope that overview of L'Hopital's rule helps you out. And if you have any questions, feel free to drop into the comments or join us on Discord. And as usual, the answers to the practice exercises will be after the outro.